Alright, in this activity we're going to discuss controller stability with a P-only controller. I'll go ahead, I've run it making sure it all works before this project, so we'll go ahead clear that. What we're going to do is, what we want to remember real quick is that when we think about stability, let's think about our transfer functions, and it's all about the denominator here. We never want to have a 0 in this denominator, because then if we have anything in the numerator, we'll go to infinity, we'll have a discontinuity. It's especially true if we go from a positive to a negative or negative to positive, then we'll definitely be crossing 0. So we're going to try to figure out how we can anticipate those actions and then anticipate what controller constants would make that happen by using our transfer functions. Again, we're going from something that seemed rather esoteric in Laplace functions, and we're actually seeing how they're used to make sure that things are stable, for example, or to make sure that we're able to simulate things in previous exercises. So it's actually pretty cool. These math subjects that may have seemed esoteric to engineers now are actually being applied. I think that's pretty cool. So, excuse me, first thing we're going to do, then there's plenty of time, we're going to clear all our variables, close everything, make sure we don't interact with any previous things we've done. We're going to set up our active directory, and then look for a step response CSV. If we do, we're going to record the we're going to recall the temperature, time, and our heater setting. Man, excuse me. We're then going to plot it. Otherwise, we're going to go ahead and do some step tests. Right here, that's all we're doing here. We're doing some step tests, and we're going to regress our parameters. That's our first step for this exercise. Once we have our parameters, we're going to turn our lab off, and then save our CSV and plot as well. After this, we're going to go ahead and regress our parameters. So we have our fmin search, which is using our objective function. Let's go down to our objective function. I want to point something out real quick. So I have this right here set to 17 in my objective function, and that's because it's the difference between the initial temperature and what's going on now. We could obviously set this up so that this initial y, this initial output, is relative to something we give it as an argument. Either way, it's really cold right now in my office, so that's why it's set to 17. But we want to do that because when we look at this sum squared of error, we want to make sure that our y measured and our, right here I have my y measured too, just to make sure that it's a stable temperature again. Our y predicted is going to be in the form of a deviation variable, so it's going to be in a delta from the current temperature. And so we do this so that our variables are similar. Now we have our y measured in terms of a deviation variable as well. Here you can see our initial state for our predicted is 0 actually, rather than 17 or 24 or anything like that. So we'll go ahead, we'll do that, and then we'll look at our P-only simulator and how that works first. So we'll go ahead, we'll run this section, look at our graph. We read successfully from our data. Is there a nice pretty graph? There is, look at that. It's a step test. What do you know? Let's go ahead with this next section now. This is where we're going to regress our parameters. Hopefully fmin search and its complement fmin con all makes sense. Fmin search is just going to do some stochastic optimization where we don't have it bounded, but we're just going to search possibilities for these 3 parameters and find ones that make sense. So here you can see we're doing pretty cool actually. This is the deviation temperature, so it's actually going to be a little bit higher. It's going to be about 17 degrees is where this starts. And we're going to go up and down and up, and you can see our prediction does a pretty good job. It gets the gain just a little bit off, I would say. You know, it should come up a little bit higher, then come down a little bit more, but that's still a pretty decent fit, I'd say. So we go ahead, we plot it. We have our Kp, our tau s, and our zeta, which is the important thing. Now we're going to go ahead and plug those in. So one thing we could actually do, if we look right here, is we already have Kp, tau s, and zeta. So I'm just going to go ahead and say Kp is equal to Kp, tau s is equal to tau s, and zeta is equal to zeta. Because they are. And then with that, we can play with our Kc, our controller gain, and see how that would affect our system. So here we go. We have our change in our set point, we have in red right here and in blue, they're kind of superimposed. We have our controller response with limits and with no limits. So as we were to move up, we'll see that we're not able to actually go over 100% heater setting. And so that's what that limit means. We have to account for the fact that our heater is bounded by the actual doable limits. So as we come up, you'll see we're executing each time, getting higher. You can see that it would go up to 300%, but it can't. Let's go up super high. Let's see what happens. Notice there's some oscillation that kind of happen occasionally. Let's go up to 15. We're still doing decently, so let's go ahead, let's configure this control, and let's go up to 30. And you can step by 0.1, default value, I like all that. So let's go ahead, set it back. Let's go up to 18 now. Let's just see how things perform at different levels. Now I've noticed some oscillations happening, but because we're pretty, you'll see those just barely for a second. We have some oscillations happening, and then they kind of calm down. So again, this is KC, it's the gain of our controller. And so the gain of our controller is going to be units of heater setting. If we go negative, you'll notice we'll go, yeah, it should predict that the temperature actually goes down. Let's go up to 30. It's going to be in units of percentage change in heater value per percent error. And so we're never going to actually equal 0, because once we were to hit 60, it would turn off the heater. Let's go ahead, just for fun, let's configure the controller, and let's just go up to 60 and see this again. We're just looking at behavioral characteristics as we increase the controller gain for our PI controller, or just for our P controller, excuse me. You can see obviously initially we're going to have very high peaks if we were not limited. And that's where those oscillations and instabilities come in, especially. We're bounded by the fact that our heater can only go up to 100%. It can't go up to 2,000%, for example. And then we're going to always just barely approach it. And that's why a PI controller comes in. It's a P controller. This is a non-integrating process, so we'll never be able to quite get there. So let's go ahead. Let's say that we want something that approaches but does a realistic job. Let's call that 17.5 for now. And let's just move on now. Let's discuss Routh arrays really quickly. What we want is we're going to analyze the denominator. So if we take our gain, as we talked about before, I'll get out my pen. We're going to take our gain in the form right here. And then if we substitute in the gains in the numerator, and then we distribute this denominator within the denominator, we're left with this form. What we're going to do with a Routh array, and hopefully you've seen this within the lesson, is that we want to get everything in a form where we have some function of s. So then we have some coefficient a sub n s to the n plus a sub n minus 1 s to the n minus 1, and it will go on. So for example, we have an s squared, we have an s, and we have these two multiplied by s. And so with the Routh array, what's going to happen is you can see, for example, this first portion is going to go right here, because that's s squared, and that's the a sub n is so n is equal to 2, and the a sub n is going to be the coefficient associated with it. Then the next one, which will be a sub n minus 1, will be 2 times zeta times tau s, right here. Then -2 and -3 go on the right-hand side. So if you just remember the first 4, I'll teach you how to remember b's and c's and so on. So last one we have is this 1 plus kc times kp. And we don't have a s to the -1. And so we already have, here, let me just get out the pen instead. This is s to the second, this is s to the first, this is s to the 0. Right here, I'll do it better without the words behind it, s to the 0. And this is s to the negative 1. And because there isn't one, the coefficient is 0. Now for the b's, a really easy way to remember this, personally for me, is I remember where the n's are, a sub n are placed. And then for the b coefficients, the way I remember it is that, let me get out my pen one more time. bi is equal to, and that's that next row right here, then you have c and so on. So b sub I is equal to this right here times this minus this times this all over the an minus 1. So, and that pattern is going to continue where it's this bottom left-hand one times the top right minus top left minus bottom left right all over this bottom left one. And that's what's going to be right here. And then the same pattern would continue where if we wanted this B2, it would be AN2, or sorry, excuse me, let me go ahead, we're just going to erase these. That would work if we wanted it again. It would be, if we wanted it for B2, it would be this one times over here would be the AN minus 4 and the AN minus 5. So, and the pattern will continue where it's the diagonals, the upper right diagonal minus lower right, all divided by, in this case, AN minus 3. So it's like a determinant almost. It's just a pattern to remember. The real concept here with Routh Array is once we have our table developed, and it's really easy just to write down the formula for the table, is that we don't want this to switch signs. Whatever sign our Routh Array is in this first column, it has to stay that sign. So let's think about our constants for a second. What are the bounds on these signs? Well, this AN and AN minus 1 have the least, especially this AN. This AN is going to be positive. It's always going to be positive because it's something squared. So that means the AN minus 2 should also be positive. So that means, and that makes sense, our zeta is always going to be positive. So that means our B1 needs to be positive. As we look at this, these we know are this quantity and this quantity is going to be positive anyway. So that means that the only quantity that could be positive or negative is 1 plus Kc times Kp. And that has to be greater than 0. Or I should say, it could be greater than or equal to 0. If it's equal to 0, I think we're still fine because it hasn't changed signs. And by the way, when I say I think, I mean we are. So, Kc times Kp is less than or equal to, we take the negative, and then it's going to be, so that's going to be less than or equal to negative 1. And then we know what our Kp is. We know that because we regressed it. So let's go up here, let's scroll up. Our Kp is equal to Kp, that's helpful. Our Kp is equal to 0.4, let's say 0.48. So let's go ahead, let's just think this through now one last time analytically. Let's get out the pen again. 1 plus Kc, Kp is greater than or equal to 0. And if I said less than before, I apologize. I'm just thinking now. This needs to be positive, so it's going to be greater than or equal to 0. We subtract over the negative 1. So that's going to be Kc, Kp. You can tell I'm not ready to be a professor yet because my mouse handwriting is not that good. And then our Kp is 0.048. So Kc must be greater than or equal to negative 1 over 0.048. And let's just go ahead, and I'll go ahead and do that in our calculator. We'll just say Kc is equal to negative 1 divided by, when I say calculator, I just mean we're going to use the command window as our calculator. So Kc must be greater than or equal to -2. That works because we weren't seeing any instability because right here, I think our lower limit was -2. So let's go ahead, just out of curiosity, let's configure this control one more time, and let's set the minimum to be -5. Now obviously, it's going to be a little bit weird because we wouldn't want to go up. But as we set 5, you see that goes negative and it never recovers. It's going to diverge and it's going to always continue to go off. Now, you can see we're reaching -6,000 degrees Celsius according to this. That's what we mean by stability. It diverges and never comes back. So we're at -2, -2.2. That's where it starts diverging and it never comes back. So that's how we do a stability analysis with the Routh Array. Let's go ahead and see what the solution was. So they have a Kp of 0.84, and so their Kc has to be greater than -1.18. So they say Kc plus Kp must be greater than 0, so I apologize. That we shouldn't have had the or equal to sign, and that makes sense if we think about it like we were saying before. If there's a 0 on the denominator, we're doing something wrong. So let's look at this root locus plot. I do not have the packages to be able to do this signal processing, but what we'll see here is that the roots will become positive. If the root locus plot looks at the roots of a function, and so as we change our k or our gain, it will look at the roots and we'll see where they either are along the line or they go along into an imaginary axis. And once that happens, we have imaginary roots, and that's where we have this oscillation. So let's cover the important points, and they're in this paragraph right here, and then you should be able to do it on your own. So these imaginary roots, an unstable controller does not have imaginary roots, so the response is expected to go from positive infinity to negative infinity without oscillation. If there are imaginary roots, we will see oscillation, and that's an important concept. So there you go, that's our activity. Thanks for watching along, and I apologize I don't have that package, but you should be able to run it just fine. Let me know if you run into any issues.